It's a great pleasure to introduce our speaker for today. We have Salim Tayou, who is a member at the Institute. And Salim will be speaking about exceptional jumps of Picard ranks of K3 surfaces over number fields.
Okay, thank you, Abhishek. Thank you for the introduction and the invitation. The title of my talk, I will explain some exceptional jumps results of Picard rank of K3s over number fields. Let me start with a definition. So let's X be a K3 surface over a number field. K, say. So a K3 surface is a smooth projective geometry integral surface which satisfies the following condition: that canonical bundle is trivial and the irregularity of the surface is zero. So H1 of X of X is zero. For example, one can think of a smooth quartic in P3 as an example of a K3 surface. Okay, so if we start with the K3 surface over a number field, we can find a model over some open subsets of the spectrum of the ring of integer of this number field. So we can somehow extend this surface over S and such that this morphism pi is smooth, projective, and the fibers are still K3 surfaces. So for every close point, little s in big S, so it corresponds to some finite place of OK. We have a specialization morphism from the Picard group of the generic fiber. So for me, it was xk to the Picard group of the special fiber, xs. Actually, I would be interested in the geometric, I will go to an algebraic closure on both sides. So I will work on the geometric special fiber and the geometric generic fiber. So this is the base change to an algebraic closure of K. And this is the base change of the reduction to an algebraic closure of the residue field, which is that algebraic closure of finite field. So this map is compatible with the intersection products on both sides, so it's an injective map. And for K3 surfaces, the Picard group is a free abelian group of some rank, which we call the Picard number. So this is the Picard number of xk bar. And this is z to the power, the Picard number of the specialization. And this injective map implies that we have the following inequality. Motivated by some questions in Hodge theory, François Charles asked the following question. What can be said about the locus in L of the set of finite places in S such that this inequality is strict? So what can be said about NL? So NL here stands for Noether-Lefschetz by analogy with the classical Noether-Lefschetz loci in Hodge theory. And let me state the first result that I will be explaining today, which is joint work with Aru Shankar, Anand Shankar, and Yunchin Tang. So we assume that we have a proper model over all the ring of integer. Mainly we can extend to K3 surface such that it has everywhere good reduction up to extend in, I mean, you allow to take finite extensions of K, but the assumption is that we can find such extension that everywhere there is good reduction.
Can we do this with a smooth quartic in P3?
Well, because this is a condition on the discriminant of the polynomial, and Yeah, I don't know for quartics, but probably, I mean, we can find family of K3 surfaces which are everywhere good reduction, but for K3s, I'm not sure. For quartics, I'm not sure. Yeah, probably it's a condition on the Jacobian of the polynomial, but I'm not sure. So the theorem we prove is that this Noether-Lefschetz locus in this situation is infinite. Okay, let me just make a remark. If the Picard number is odd, then in fact, this Noether-Lefschetz locus is always equal to S, the whole set S without any assumption, independently from our theorem. And the reason for that is the Tate conjecture. So the Tate conjecture predicts that this rank of the reduction is even actually, because it's equal to the multiplicity of roots of unity of the Frobenius action at this place acting on the second état cohomology group of the K3 in QL1. And in fact, the rank of this group is 22. And since the Frobenius action is semi-simple, then this multiplicity is also even. Yeah, so the whole rank is even, and yeah, and the roots they come by pairs because we have a quadratic form on this H2. So the cardinality of the roots of unity is even. So yes, this implies that you have always a strict inequality.
I don't understand. So, I mean, the multiplicity of the eigenvalue 1 has no reason to have any parity.
Sure, yes. So here we're allowing extensions of the field, the roots of unity. So those which are not roots of unity, they come by pairs. Lambda, if lambda is a eigenvalue, then 1 over lambda is also an eigenvalue because we have a quadratic form, a pairing. And so those which are not of unity, there is an even number of them. So the complementary, there's an even number of them. Make sense?
Okay.
Yeah. Okay, and if this Picard number is even, then there are some situations which are completely understood from the Hodge theoretic point of view, where this Noether-Lefschetz locus can be of density 0. So what our theorem proves that even if this locus is density 0, it is infinite by our theorem. So the first question one might ask is why we are interested in such questions. Let me give a first corollary of why these questions were studied. So there is for K3 surface, if you have a K3 surface of an algebraic closed field, let's say over K bar, and we suppose that X has a model over K or over an extension of K, which is has everywhere good reduction. So with a model with everywhere good reduction, then X contains infinitely many rational curves. Okay. In fact, we have an alternative. Either X contains infinitely many rational curves, or so one of the following stuff, or X has infinitely many super singular reductions. Okay, so this is related to the conjecture saying that if we take a K3 surface of an algebraic closed field, then it contains infinitely many rational curves, and using this theorem, we can say this alternative. Yeah. Let me also, so I should also add that this like the first statements have been proved by completely different method. By the work of Shen, Gunla, and Litke. Yeah, so the method they use are completely different from ours. Okay, so let me also give some other known results which have similar flavor, like previous.
I'm a bit confused. Can you scroll back and see? I want to see what the statement is. It's A or B, then either A or B.
Yeah, it's either A or B. If
how can they prove A without having B by different methods? What do they prove?
So they prove that this A is true.
But then logically, why would you care about B? If the theorem says either A or B and A is true, then why do I care about B?
I mean, what we prove is that what our methods yield is that either A or B is true. But if A is false, then B is true. But their method yields that A is true. So at the end of the day, we now know that this A is true. But not by our method does not prove that A is true.
So their theorem is stronger than yours?
Yes.
Okay.
And what is known about the possible infinitude of supersingular reduction? And what do you mean by supersingular, by the way?
So by supersingular, I mean that the Picard rank is 22.
Okay.
Yeah. And about this question, I think nothing is known. Yeah, basically. Okay, so now I will mention, I mean, at least, of course, if we suppose that the Picard rank is sufficiently small, of course, if we take a Picard rank, which is 20 or, and then, then the jump will be automatically supersingular. But like, for example, if we take Picard rank sufficiently small, 2 or 4, then yeah, nothing is known in this situation.
Sorry, Salim. So does their result imply that B cannot happen, or? No,
they say nothing about B. I mean, they work purely in the complex geometric setting.
So B is unknown, whether
B is unknown, yeah. B is unknown.
I see. Okay.
Are there examples where B happens?
So if you take a K3 surface with Picard number 20, the only possibility for the jump to happen is the 22. Yeah.
Thanks.
If you took an abelian surface with complex multiplication, the corresponding Kummer surface would be like.
Yeah, exactly. Yeah.
Like this.
Yes. So yes, I will mention some previous work which have similar flavors and actually which inspired our work. So the first theorem is due to François Charles. And he proved the following things. Actually, he explains this result actually in this seminar. If we take K a number field, and if we take E1 and E2, two elliptic curves over K, then the set of primes inside OK where the reduction by taking the reduction to the geometry and the base change to the geometric fiber are isogenous. Well, this set is infinite. Of course, here I assume that they have good reduction, and So, so this, yes, our results compared to this one by taking the E1 times E2 and taking the associated Kummer surface, then we can, we get a K3 surface, and this is somehow the link between the two theorems. So here, of course, and also here, there's no assumption on the bad reduction. He gets the theorem for any elliptic curves. We hope also that in our main theorem, we could remove this everywhere good reduction hypothesis. And one further remark is if E1 and E2 are not isogenous over K bar, so not generically geometrically isogenous, then let me call again this set, and L has density 0. But still it's an infinite set. Another theorem which has a similar flavor has been proved by Anat, Shankar.
Oh, but wait, if they are isogenous, then the set has density 1.
Oh, sorry. Yes. Yeah. If they are not. Yeah. If they are. Yeah. Sure. Yeah.
So it's this kind of 0-1 theorem.
Yeah.
It's like the worst way to tell if two elliptic curves are isogenous.
Yeah. And yes, so another theorem which has similar flavor by Anat Shankar and Yun Chin Tong says the following. If you take an abelian surface with real multiplication, meaning that there exists a quadratic real field over Q which embeds inside the endomorphism algebra of A, then the set of primes of OK, where A has good reduction, of course, and the geometric special fiber is isogenous to a self-product of an elliptic curve, this set is infinite. Yeah, of course, here also the same remark is that if A bar is simple, then the set has density 0. But still, it's an infinite set. So actually, our method also yields the following theorem, the method of the proof. If you take an abelian scheme over, okay, so an abelian surface with everywhere good reduction, then the set of primes where the geometric special fiber is isogenous to a product of two elliptic curves, not necessarily the same one this time. Well, this set is infinite. So yes, so all these results have the same flavor. We are working with some K3 motif in some Shimura variety that I will explain later, and we prove that some set is infinite, and they have actually motivations coming from complex geometry that I will explain now a little bit. Oh. So I'll talk a little bit about the complex picture. For this, let's consider a family of K3 surfaces. Now, X and S are a complex variety, and assume for simplicity that S is a curve which is quasi-projective. over C. And for little s in big S, we denote O of S, the rank of the Picard group of the K3 surface, which is the fiber of this family at little s. And the classical Noether-Lefschetz locus here is the set of elements such that this Picard number, OS, is strictly bigger than the minimum over the family. So to speak, the generic Picard rank. And
is the minimum over the family different from the Picard rank at the geometric generic point of the curve?
I think here they will be the same. Up to taking some finite total cover, say, they will be the same. So the first result known in this direction is by Borcherdt, Katsarkov, Pontev, and Shepard-Baron. Okay, take me a whole line, it's all right. In 98, which says the following thing: if the family is non-isotrivial, so this is a necessary condition, otherwise this locus is just empty, and S projective, then this Noether-Lefschetz locus is non-empty. So yeah, the proof relies on the construction of Borcherdt by of an automorphic form on the moduli of K3s and showing that this Noether-Lefschetz locus is ample inside the moduli of K3s. I will say a few more words on this later. A few years later, there is a proof. There was a proof by Green and Ogizo, 2003, I guess, which assume only that P is non-isotrivial, and then this Noether-Lefschetz locus is dense for the analytic topology. So there is no assumption on projectivity or whatever. They prove it over small variation like over disks. In my thesis, I proved that actually one can have a final result in this following sense. Assume they always that pi is non-isotrivial. Then this Noether-Lefschetz locus is equidistributed in S with respect to some natural measure which is given by integration of the curvature of the Hodge line number. I will make precise the statement once I will talk about the Hodge line model, but yeah, the general idea is that if we look at the set of points where there's a Hodge class of square n, that's where a Hodge class of square n appears, then it gives us a finite set inside S, and if we count points in this finite set, then in any open subset, then we find as much as it's proportional to the volume of this open subset. Anyway. So
does S have to be projective here? Or?
No, there's no assumptibility of projectivity for any S. S is quasi-projective here. But still an algebraic family, of course. Yeah, so our main theorem is can be seen as the main theorem is a mixed characteristic analog of these theorems, of these results. Especially the density one. Okay. Okay, so now I will give some sketch of the proof of the main theorem, and before that, I will explain what's the proof in the complex picture, because it will give us a lot of idea of what happens in the mixed characteristic situation. So consider so let's pi be a family of K3 surface over a smooth quasi-projective curve S, so over C. And we consider here a line bundle over X, which gives a ample line bundle, so it's a polarization. And for simplicity, assume that the generic Picard rank is 1, so the minimum over the whole family is 1. So that there is only the Chern class of this line bundle that appears as a Hodge class in a very general member, a very general element in S. I will also assume that this family is non-isotrivial. Otherwise, I mean, yeah, as I said, the Noether-Lefschetz is empty. So starting from this data, we get what we call a variation of a Hodge structure in the following way. We consider first a local system over S, which is given by the second derived direct image of the local system, the constant system Z over X. So this is basically the local system that's whose fibers is just the H2 of the K3s. These are the fibers, and they glue together in this local system. And actually, I will consider a sublocal system of this one, as we know that the first Chern class of L gives a Hodge class everywhere in the members of the family. So we consider it's orthogonal with respect to the Poincare form inside this local system, and we note this one as VZ. So this is a local system with a quadratic form. Quadratic form Q. Actually, this quadratic form Q, the fiber at every point will be isomorphic to some lattice, say LQ, which has a signature 219. Okay. What is most important here is the 2. The 19 is just some numerology. If you have chosen like other generic Picard rank, then the 19 will have dropped. And for different, so in general, there will be an integer B here of different values of B. We will get, for smaller value, we will get either families of elliptic or products of elliptic curves or products of abelian surfaces. But let me focus now on 19. So yes, this is the first thing. We get a local system. Then,
is this a point you want higher rank? Why is it 2? Why is it 2 important? I mean, you can't.
2 here is, so now we have the work in a Shimura variety. The moduli space embeds in a Shimura variety of orthogonal type.
Okay.
Yeah.
Okay.
Yeah.
But I'm sort of trying to understand whether any of your equidistribution theorems are following from Ratner kind of argument.
So equidistribution, in fact, can be obtained for even for if it's not 2. Yes, true. Yes.
But it uses Ratner?
Yes.
Okay.
Yeah. Yeah, I'm not going to talk about that today, but yes. And
I mean, to use Ratner, you probably need that some subvarieties generated by unipotents, SL2s. So that's not where the 2's coming in. That's all I was trying to. Yeah,
so to use Ratner, we only need to ensure that this B is not 1. We are not in 2.
Okay,
1.
not in alpha.
Yeah, okay. Yeah. So the subvarieties will be associated to group generated by unipotent. Yes. Yeah, so we have a local system. We have also a holomorphic filtration. So we have a vector line bundle F2V, F1, and F0, which is just the local system tensored with the sheaf of holomorphic functions of S. So this is a holomorphic filtration. And this here is the Hodge line bundle that I mentioned earlier. And of course, we have an integrable connection which satisfies the Griffith transversality. And this data, so this local system, this filtration, the quadratic form and the connection which is there. This is a variation of Hodge structure, what we call of K3 type. K3 type referring to the fact that F2 is a line bundle, and this is of weight 2. The variation of Hodge structure is weight 2. So yes, as before, let LQ be the lattice, which is the fiber of this local system, which you can describe explicitly, but I won't. And we consider the period domain. D, which is the elements and the lines in LC, which are isotropic. And they satisfy this positivity condition. So this domain D actually just parameterizes the weight 2 Hodge structure on L, which are polarized by Q. And this is simple, I mean, easy to say. If we have a weight 2 Hodge structure, it decomposes as L20 plus L11 plus L02. And this LT0 actually will define a line in D. So we have this correspondence. So starting from this family of K3 surfaces, if we take the universal cover of S, I mean, this is a classical construction of the period map. I'm just, here the local system trivialized. So just the constant system L. So this family of variation of Hodge structure can be just a variation of Hodge structure on a fixed lattice L, and so we get a period map to a point S just to associate the associated filtration. That's X. And it factors here. We can go to the quotient by some subgroup gamma inside the orthogonal group of L. And here we get a period map. Well, this map is holomorphic by Griffith's work. And moreover, this D mod gamma is actually an orthogonal Shimura variety. And so it has an algebraic structure. So it's algebraic quasi-projective by Bailey-Borel. And moreover, this by a theorem of Borel, this period map is also algebraic. Yeah, so the idea to study the Noether-Lefschetz locus is to intersect S inside this D mod gamma with the family of divisors that we call the special divisors, which have a lot of interesting and nice arithmetic properties. So they are defined as follow for any integer M which is negative, let Z of M be the union over all the elements in the lattice which have square M of the orthogonal of this element X, so the, actually let me call them lambda. Of all the elements X and D such that X is orthogonal to lambda. So this is somehow the set where lambda is a Hodge class. We are taking a union over all the elements lambda in L with square M, and we quotient by this arithmetic subgroup gamma. So Zm is again an algebraic subvariety of D mod gamma, and the intersection of S with Zm is exactly the set of points S in S, such that it exists lambda, which is a Hodge class, and Q of lambda is equal to M, at least. So this, yeah, set theoretical intersection is this one. So actually, this is not true because we count, I mean, if you count with multiplicity, every point S is counted as many times as there are Hodge classes of square M that appear on it. We also introduced the Hodge line bundle, which is defined just by restriction. We take the O minus 1 restricted to D. This has a gamma equivariant action. We take the quotient by gamma, and we get here the Hodge line bundle. So of course, the pullback of H is just F2. The pullback to the curve. So our theorem due to Borchardt asserts that this, when you form the generating series of the special divisors, okay, in H dual here, for M negative of this special divisors, phi of tau, where tau is an element in the upper half plane. Well, this is it can be seen as a generating series in peak D over gamma times C double bracket Q. This is a component of a modular form. So by mean a component, there is a vector valued modular form, which this one appears as a component of the vector valued modular form. So this result has the nice arithmetic consequences that if we take S projective, so assume that S is projective, that if we take the intersection of S with the Zm.
What's the weight of this form? It's a regular holomorphic.
Yes. It will be 1 plus 19 over 2.
And the level? Are you making vector value?
Yes, yeah. So I'm saying vector value, so it will be full level for metaplectic group. Yeah. So yes, by studying the space of vector valued modular forms of weight 1 plus 19 over 2, one can derive the estimate that this intersection grows as absolute value of M to the power 19 over 2 times the intersection of S with H. And this is just the volume of S in the sense I defined precedently with respect to this measure. So yes, this just by studying this divisor, we get a quantitative statement of how the Hodge locus grows.
Sorry, what is the meaning of the approximately equal sign here?
So I will say there are constants C1, C2 strictly positive such that this S times dm. Sorry. can be put between C1 and C2.
I'm a bit perplexed here. The Borchert's theorem had nothing to do with S.
Yes, has nothing to do with S. I'm just giving a direct application of this. Yeah, sure.
And so how do you apply it?
So S is projective. So I just take the intersection of this modular form with S. I get now a vector valued modular form.
Mm-hmm.
And now this vector valued modular form lands in a space of vector valued modular form, which has Eisenstein series and cospedal forms.
How do you know it's not zero?
Because the intersection of S with H is non-zero, because H is an ample line bundle restricted to S.
Oh, okay. Okay, I see. Thanks.
Yeah. So yes, here, I mean, exactly, we get a formula, which is a precise formula of m to the power 19/2 times some product of singular series. I mean, I want to explain what these are, but for high values of, I mean, we don't have like a precise growth rate of the singular series, but we can still say that they are bounded by some positive constant. That's why we don't get really a precise estimate by just some upper and lower bound, which are of the same magnitude. Yes, so now, okay, let me move to the mixed characteristic situation and see how the picture changes a little bit from the complex picture, but the ideas will be...
Sorry, when you said your main theorem on your thesis, no, I didn't say main theorem, you said it was a theorem in your thesis.
Yes, yes.
You said something was equidistributed. Did you mean in this sense, or did you actually have an asymptotic?
Yeah, I have I mean, I have an asymptotic in the sense I can give a precise meaning which is equal here.
But it's just using Borchert's.
No. Like so, this is like somehow the global counting, and now to prove equidistributed, we should take any small open subset and prove that there are as many. So if we want to prove equidistributed, we take any delta inside S, and we count.
Okay, so this is giving you the global count and the local. Yes. That you will use rat now.
Yeah, exactly. Yes.
I just want to know where it's used.
Yeah. Okay. So let me give that then a brief idea. So so if we take a fixed delta over S, we have a fibration over delta of S and lambda, such that lambda is in say in V11 at S. It's a real 1-1 class. So this is give some kind of, and assume that Q of lambda is equal -1. So this gives some kind of fibration above delta, but just by sending the point S lambda to S. And the fiber are spheres inside so this is over R. Are spheres over S. And by the parallel transport map, so if I choose delta simply connected, I can project this set to just the quadric in LR such that Q of lambda is equal -1. Because, you know, I'm taking, this is just by parallel transport. Like if I have so delta is simply connected, then we can trivialize the local system and see every class here 1-1 as just an element which lives in this space. And inside this space, I have all, for every integer m, say, negative in my conventions, I have the set of elements lambda in R such that square root of -m times lambda belong to the lattice. So this is just, I see the elements in the lattice, I normalize them, I obtain points in this quadric. The equidistribution theorem will come from saying that this, as m goes to infinity, this set here is equidistributed in this quadric. And this is, so I don't hear you, Peter. Yeah.
Yeah, the equidistribution is a relative statement. The Borchardt just gives you the growth, crude growth.
Yes.
And then this gives you, okay, that's fine. That's you don't have to say more things.
Okay. Okay, so let me now move to the mixed characteristic situation. Okay. So here the idea will be the same. So first, the first step is to see that there are of course more complications, but the first step is to see that this D mod gamma is the C points of some algebraic variety M defined over Q, so to speak, the canonical model, which is due to the work of, I mean, in this case, to the work of many people. I mean, Deline, start from Deline and Min and André and others. And then, of course, we are studying a situation over the ring of integers. So we want to extend this Shimura variety over a whole spec Z. And here, it is the important work of many people, also Kissin, Medapuzipera, Vazju, although I'm surely forgetting a lot of names, but yeah, there are a lot of people who contributed to this thing, so that we can find a model over spec Z, which is flat, normal Deligne-Mumford stack. Of course, these models can also with the models of all the special divisors that I defined earlier. They themselves also extend over spec Z. And so our theorem, so just I recall our theorem, we start with a family of K3 surface over S, which is spec OK. So here again, we have a period map, which goes from S to this model, which is due to the work of Rizov and Medapuzipera. And the basic idea is we want to prove that the intersection of S with Zm, we take the union over all M, is infinite. I mean, we want to prove that. And here, so we want also to perform intersection theory, and the natural setting to perform intersection theory in this is Arakilov intersection theory. So in a nutshell, we define. I will define briefly what are the tools here. We define a first arithmetic Chow group of M, which is formed by the direct summand of the pair AG, where R is a Cartier divisor and G is a green function. And I take the quotient by the divisor of rational functions where the green function is simply minus log of f squared. So by a given function, I mean just a C-infinite function on the complex point, which has logarithmic singularities along the divisor AC. And now by work of Borchardt and Brunier, we can attach to this special divisor Zm a green function in some specific way, Gm, so that it becomes an element of this first Chow group of M. And yeah, the most interesting result in this direction is that the modularity result, as I mentioned earlier, also stays true in this setting by extension of Borchardt result by Howard and Madapuzipera. Yeah, there's also a way of extending the Hodge-line bundle, I mean, endow it with a Hermitian metric so that it becomes elements of CH1. And if I form the generating series over Z hat minus M Q to the power M, then it's again components of a modular form. Let me just write modular form for laziness. And the similar story we can perform now the intersection with the arithmetic intersection with the curve S. So we have a map from CH1 of M to the CH1 of S. So it's crucial that S has everywhere good reduction to be able to construct a degree map to R, a well-defined degree map to R, and so that we can take the intersection of S with Z hat M. So this will be simply the degree of the pullback under the period map of the divisor Z hat M in say CH1 of S.
So where are you using everywhere good reduction?
To construct this degree map. If I mean, it's basically the product formula. If we don't have if we miss some places, then there's no well-defined degree map to R. Yeah. Yeah. So let me denote this this quantity by the height of S with respect to Z hat M. Z hat M, and this height can be decomposed as a sum over finite places of the contribute. So the multiplicity of intersection of S with Z hat M at the place P times log the norm of P plus an Archimedean contribution, which is the evaluation over all embedding of K and C of GM evaluated at S sigma. Actually, I think there is here 1/2. So, okay, so the Borchardt's modularity results imply that this term, as we saw in the complex setting, is something. So it's approximately, or no, it's it. Okay, here it will be a big O of M to the power B over 2, which is enough here, because we don't know that the height of this vector will be. Anyway, I didn't say anything, but being a big O of M to the power B over 2, that's what we need. And so we will analyze, we want to prove that the set of places that contribute to this sum as M varies are infinite. So assume for the sake of contradiction that there are only finitely many such places. So that this sum star, so there exists an R such that for every M, the sum star is just a finite sum from E to 1 to R of the contribution at the finite place Pi, log of norm of Pi. So what we do first is understand the behavior of the green function. We prove that this GM of X sigma is approximately M to the power B over 2 log M. So here we have a contribution logarithm of log m, and plus other contributions, which are big O of m to the power b over 2, or let's say little o of m to the power b over 2 log m. Yes, so to be precise, we don't prove this for any m, but for most m's in a precise density sense.
What are you using to do something like this? Are you using, you need clearly some estimates of resolvents or something?
So
kernels, or what are you using?
So here we're using the explicit expression of the green function. So there is an explicit expression of this green function.
In terms of theta functions or what?
In terms of it will be a weighted sum over the elements of the lattice, but there will be a contribution. So this term here appears as the derivative of some function. Actually, this term is not really what causes the issue. The issue here is to prove that we have a little o here, and here indeed it appears some kind of theta function as a sum over elements of the lattice lambda of the distance of the point x to the divisor. And the issue is that the issue that can happen is that the divisors could be arbitrarily close to the point such that this estimate here will explode. So this is what we want to avoid by working with most m's. Sorry. This is what we obtain by not working with a specific m, by averaging. We control this term.
But are they subtle? You're talking about Green's functions. Is it a local question in the end, or is it some?
Yes. At the end.
You're not having to study like in Folting's delta function on abelian varieties, which has a very subtle behavior into the cusp. Nothing like that.
No.
Or
no. It's rather it's a local question. So this point x sigma defines a point inside the period domain. Mm-hmm. Let's say we're working locally, and yes, and you have all for any given integer m, you have all this special divisors given by.
This is a very interesting way of proving the infinitely many primes of some type, right? Yeah. You have a formula, local and global, and then you're saying if there are only finitely many primes, everything else is going to blow up. It's unusual. Although I think they used it in another theorem like this, Tang, right?
And Nance and Yunchin in their proof of abelian surfaces.
Right.
Abelian surfaces case, yes. And Francois for the products of elliptic curves.
Right, for Francois. Yeah.
Mm-hmm. Yeah, indeed, yes. So this, so the thing is, we have all these divisors that come close to x sigma, and the idea is to say that these distances do not get too close in average.
Should I ask you now or later? How many primes do you get? Maybe later.
Sure, okay. Maybe when she
after your lecture. After your lecture, we'll see how many primes you get.
Yeah. Could you give us a kind of some sort of understanding of where this mb over 2 log m comes from?
The mb over 2 is the coefficient of an Eisenstein. If you take an Eisenstein series of weight 2k, then its main coefficient grows like, its mth Fourier coefficients grows like m to the power b over the weight minus 1. Basically, roughly the idea.
And the log m?
And the log m, yeah, this is like somehow the miracle that makes things, at least in the arithmetic setting, there are logarithms contrary to the geometric setting. And yeah, I think it appears in the computation, but I don't know if I have a better explanation.
If there's some toy model with CM points in the upper half plane that has this behavior?
Sorry?
Is there some simple toy models? Oh, sorry. Anyway, you're short on time, so I'll ask later.
Okay. Anyway, so I have very last things to say. So yeah, okay. Now we know how to let me go back to the formula here. What I explained is that this term is very negative. It's like m to the b power 2 log m. This term is at most m to the m to the power b over 2. And the last step is to prove also that this local contribution are themselves little o's of m to the power b over 2 log m. So yes, so last step. This contribution that are fixed prime are also little o's of m to the power b over 2 log m. Yeah, so this is also used. So this is used a geometry type of number argument, and we don't prove it for every m again. For only for certain sets of good m's outside of some sets for which we define the density, and we saw that for a precise notion of density it's 0. And so yes, the final piece is there. So this is a little o of m to the power b over 2 log m. And so there cannot be finitely many places, because otherwise this formula does not stand. We have a term that grows fast, and there's nothing to compensate the growth of this term that grows very fast. So there should be infinitely many places.